So hi guys, welcome to my channel. So today I'll be solving this GFG problem of the day, which is merge two BSTs. Okay, so let's read the problem and try to approach this. Okay, so before that, the difficulty is mark medium, and we can see that the code is also very big. But again, just bear with me till the end, and after I'll explain how to approach this problem. The code will be like cakewalk for you all, and you all can write it by your own. Okay, so now let's see what we have to do. Okay, so given two BSTs, return elements of merged BSTs in sorted form. Okay, so what is BST? Binary search tree. Okay, as the question is saying merge two BSTs, and the statement is also very clear. Okay, so we are given two binary search tree, means 5, 3, 6, 2 and 4, and 2, 1, 3, 7 and 6, and we have to merge these two BSTs and we have to give the output, and output should be also in the sorted order. Why question is saying that output should be in the sorted order? I'll be explaining this. Okay, so let's see with this test case, what we have to do is we have to merge these two BSTs. Okay, so before merging these two BSTs, let's see one or two properties of BSTs. So the first property is left of a particular node will be smaller than root, and right will be greater. Okay, so this is the one of the two properties. Okay, these are the two properties. Okay, so now let's see another property, which is in order of BST binary search tree is always sorted. Okay, in order of BST is always sorted. Okay, so this is the third property, means if we find the in order traversal of this binary search tree, so it will be always sorted. You all can see that. Okay, in order, first 2 will come, then 3 will come, then 4 will come, then 5 will come, then 6 will come. So the sorted order will be 2, 3, 4, 5 and 6. Okay, you can look here also. 1 will come, 2 will come, 3 will come, then 6 will come, 7. Okay, so 1, 2, 3, 6, 7, sorted order. So this is the very important property of binary search tree. Okay, so just remember one thing, whenever you got the question of binary search tree, just write these three properties somewhere and then start solving this problem. Okay, so you all will be very clear that why the question is demanding for this sorted order like this one. Okay, so return elements of merge BSTs in sorted order. We don't have to sort it particularly, but if we write the correct code of like merging these two BSTs, then whatever BST will be made by merging these two, automatically these two BSTs order will be sorted, in order will be sorted. So just we have to find the in order, or will be like okay with the solution. Okay, so now let's see. Okay, so first approach of solving this problem is just store all elements of BST1, BST2. Okay, so just store all the elements of BST1 and BST2 and store it in the answer vector and just sort it. Okay, so let's see the approach one. What I have told you is first start iterating the BST1 and take the nodes out. Okay, 1, 3, 4, 5, 6. Traverse the BST2 and take the node out. 1, 2, 3, 6, 7. Now sort it and store it in the answer vector. So after sorting, it will be okay. So in approach 1, let me revise once more. In approach 1, what I have told you, traverse the BST1, store the nodes, traverse the BST2, store the nodes, sort the like these data, this is stored in answer vector, sort it and finally return the answer. Okay, so we have returned the answer. Let's check, is this correct or not? 1, 2, 2, 3, 3, 4, 5, 6, 6, 7. Okay, let's see. 1, 2, 2, 3, 3, 4, 5, 6, 6 and 7. Okay, so we have found the answer. So we can see that this is how we have calculated the answer for approach 1. But the catch here is, so we are told to use the auxiliary space as height of BST1 and height of BST2 and m plus n. If we traverse the whole nodes in the BST using recursion, it will be taking the recursive call stack and it will take the auxiliary space as big of n. Okay, but what we are told that as we have to use the height of BST1 and height of BST2. So we will be solving this problem with an iterative way. Okay, so let's try to solve this problem with approach 2. So what we will be doing in approach 2, we will be using two stacks. Okay, done. Stack 1 and stack 2. Okay, and this is st1, this is st2. Okay, okay, and finally storing it in our answer. Answer is equals to empty. Okay, so now let's traverse it. Okay, so what are the steps we are going to follow is, this is the root node. Okay, so let's just put into the stack. Okay, and whatever nodes we are pushing into the stack, or whatever node we are currently standing in, we have to go its entire left and like simultaneously pushing it into our stack. Okay, so let's push it. 5, 3, 2, we are pushed. Now you can see that this is BST. So whatever root we are standing on, the left is always smaller. Okay, you all can see with this, left is smaller, right is greater. Okay, done. So 5 I have pushed, 3 I have pushed, 2 I have pushed. Now stack follow the LIFO order, last in first out. So it will be storing it in the like reverse order. Okay, so 2 will be first, 3 will be first, 5 will be first. Means we got the sorted order kind of a thing. Okay, so now let's store the elements in BST2 from BST2 also. Okay, so if we are standing at 2, we'll be pushing 2 in the stack. Okay, we are pushed. Now if we are standing on any particular node, we'll go its entire left while we not reach the null, and simultaneously storing the nodes. Okay, so 2 we have stored, 1 again I have stored. Okay, so now after going its extreme left, we have reached null. Now we will be comparing that whether stack 1 dot top is less or stack 2 dot top is less. Okay, so we can see that stack 1 dot top is less. Okay, so let's pop it, store it in our answer, and while popping we'll be checking that whether its right element is present or not. Okay, so if its right element is present, then we will be again like pushing the right element and go its entire left and push the entire left element in the stack. Okay, so just see and like observe the whole diagram, and after that you will be very clear. Okay, so we have removed 1, done. Now 2 and 2, which is smaller, both are equal. So what we'll be doing, let's pop it once from stack 1, we will be pushing 2. Now 2's right is present. No, 2's right is not present. Okay, so just remove it. Now again pop 2 here. Okay, 2 right is present. Okay, 2's right is present, so just pop and write 3. And what I have told you, if I push any of the node in this stack, I'll be go its entire left and simultaneously pushing the nodes which is present entire left of it. Means the path which goes to entire left. So entire left, 3's left, which is empty, so no need to push the elements. Okay, so we have taken out 2 from stack 2 also, stack 1 also. Okay, now what is the minimum element? Okay, so 3 and 3 both are again equal, so let's start popping 3. Okay, so 3 from stack 1, we have popped 3. Let's write it in our answer. Now 3's right is present. Okay, 3's right is present, 4, remove it, pushed 4. Okay, 4. Now 4's whatever nodes we have pushed into our stack is, we have to go its entire left. Okay, I'll be writing these steps like what are the steps we are following. So just wait. So what are the nodes to the entire left which is present? There is no node which is present. Okay, so just leave it. Okay, so now see 4 and 3, which is minimum. Okay, so 3 is minimum, so remove it. Okay, so now let's push 3. Now 3's right is present. Okay, 3's right is present, push 7. Okay, 7's left is present. Yes, 7 left is present. What I have told you, whatever I have pushed, push its immediate right. Okay, again, whatever I have pushed in this stack, push its immediate right. I have pushed it immediate right, and go its entire left and push it into the stack. Okay, so I hope this is clear. 7 and pushing 6. Now let's remove this. Now with 4 and 6, what is minimum? 4. So what we'll be doing, we'll be writing 4, remove 4. Okay, done. 4's right is present. No, 4's right is not present, just remove it. Now 5 and 6, which is minimum? So 5 is minimum, so pop 5. Okay, so one thing to be noticed here is, very clearly or very beautifully we have stored all the elements towards like left of which is towards the left of 5, all the elements 2, 3 and 4 before reaching to 5. Okay, that's why I'm saying that whatever nodes we have pushed into the stack, if the work of that node is completed, just push the immediate right, so that before visiting this you all have explored all the left part of this particular node. Okay, so I hope this is clear now. So now 5 is minimum, so remove 5. Before that, push 5 into the answer. Now check that 5's right is present. Okay, 5 right is present, so I have to push this 6. Now whenever I push 6, what will be seeing? Go its entire left and check that whether it's like nodes are present or not. No nodes, so leave it. Okay, so now within 6 and 6, which is minimum? Okay, so let me write this as this. Okay, which is minimum? Both are like equal, so let's remove one by one. 6 remove, 6 push here, 6 entire right, 6 right is present. Okay, no, 6 right is not present. Okay, leave it. Now come here, 6. Okay, push 6. Okay, done. Now you all can see that stack 1 becomes empty before writing this. Okay, so after taking out 6 from stack 1, you all can see that stack 1 becomes empty. If one of the stack becomes empty, that means that we have traversed the whole nodes in the BST1. Means now only what we have to do is just pop the element from the stack, check its entire right and go its entire left and push it into the stack, and slowly pop the elements from the stack and write it in our answer. Okay, so just remove 6. 6 right is present. No, 6 right is not present. Okay, so just done it. 7 right is present. Okay, 7 right is not present, so just pop it and remove it. Now you all can clearly see that we have found the answer. And what is the auxiliary space complexity demanded is height of BST1 plus height of BST2, and you all can see that at one go we only storing the height of the BST1, not more than that. Okay, so we have achieved the space complexity, and you all can see that 1 2 2 3 3 4 5 6 6 7. Okay, 1 2 2 3 3 4 5 6 6 7. So now let's see some steps what we are actually following. Okay, so initially what we are doing, push the root and its entire left. Okay, what are the nodes that are entire left of that root in the from BST1 and BST2? Okay, done. Now compare the top element from both stack and whatever is minimum. Okay, so whatever data which is present at the top of the stack 1 is less than stack 2. Okay, so we will be doing some step. Now stack 2's top data is less than stack 1's top data, so we'll be doing some step. Else we'll be doing the step in from both the stack. Okay, from both the stack. And finally what we'll be doing, while stack 1 is if stack 1 becomes empty, means we have to only follow stack 2. Okay, done. If stack 2 becomes empty, then we have to only follow stack 1. Okay, done. Now let's see the code. Okay, so what I am doing here is I have created a store left, in which what I'm doing, I have passed a root and I have passed a stack. I'm making a node star variable and assigning it to root. Okay, done. Now while current is not equal to null, I'll be pushing the current node in the stack and going current is equals to current ka left. Done. The store left is doing only like very simple thing, that store the root and go its entire left and simultaneously pushing the nodes into the stack. Okay, done. Now this is our main function, like void int merge. Okay, so what we are doing here, so initialize to stack, initialize the vector answer, and initially we are standing on 5, we are standing on 2, push 5 and its entire left nodes. Okay, store left means root 1, it will be push 5 3 2. Now store left root 2, it will be pushing 2 and 1. Now our loop will start while stack 1 is not empty and stack 2 is not empty. Do the following operations. Okay, done. Now if stack 1 dot top data is less than stack 2 of dot top data, means whatever elements which is present at stack 1 top is less than stack 2 top, then what will be doing, I'll assign the current at stack 1 top. Okay, and pop the element from the stack. Okay, done. Means what I've told you means whatever elements we are present in the stack 1 will assign that current and pop that element from the stack. Now I'll be pushing that data into the our answer vector, and whatever element we are currently standing on will push its right and give the stack 1 and tell that whatever element. Okay, so let's see with an example. Okay, so 3, we are standing on 3, will be giving 4 and tell that go and explore its 4's left. Okay, so same I have done. We are standing on current, I'll be giving 4's right. Okay, so I'll be giving 3's right, means 3's right, and giving stack 1 and tell the store left that whatever elements that are present on the left of the current node, then store it in the stack. Okay, so if stack 2 dot top data is less than stack 1 dot top data, then assign current to stack 2 dot top and stack 2 dot pop, means remove that element. Okay, store it in our answer, and finally store left, what we'll be doing. Okay, so again, if we are standing on 3, it will pass the current left, current right, means 7, and tell that okay, so store all the elements which is left, towards left of that that node. Okay, so again doing that. Now else condition means the stack 1 dot top data double equal to stack 2 dot top data, means both elements are equal. If both elements are equal, then we have to explore both the elements. Okay, so current 1 is equals to stack 1 dot top, current 2 is equals to stack 2 dot top. Okay, then simultaneously pop the elements from both the stack. Okay, done. Now push both the data into the answer vector. Done. Now whatever element which is present at the current right, pass it into the store left, so that it will be taking out all the elements which is towards the left of that. Okay, done. Now same do it with the current 2. Okay, done. Now after completing the while loop, what we'll be doing, either the stack 1 becomes empty or stack 2 becomes empty. If stack 1 becomes empty, then we will be following this this step. Okay, it means that there are still elements present in the stack 2, so we have to do same thing which we are doing. Current 2 at stack top, pop the elements, store it in our answer, and pass the currents right, and tell that whatever elements which is to the left of the currents right, then store it in the stack 2 and finally explore that. If stack 2 becomes empty, then what we'll be doing, here I have told you, if stack 2 becomes empty, then we'll be doing this step. If stack 1 becomes empty, then we'll be doing this step and finally returning our answer. Okay, so let's run this code. Okay, so let's submit it. Okay, so we have passed the test case. So this is how we are solving this problem. So I hope the approach is clear and the code is also crystal clear. So thank you for watching and having patience. So thank you.